Do you put the presentation on your laptop? I think it's more easy if you have the USB.
We can move the connection.
Okay.
The problem is that
No, deve essere collegato con...
we are broadcasting the session, so can you copy in a USB?
Yes, of course.
Questa idea?
Non lo so, no. Vedi. C'è anche questo. Virtuale non c'è nessuno. Virtuale non c'è nessuno. Quindi sto solo con loro. You are the other presenter, right? Yes. Did you upload the presentation here? Yes, it's already here on the desktop.
I know what cannot be recognized. The step.
Try with this. Does it work? Okay, can you send me a message?
Yes.
Gmail. I will write you. Okay.
Is the presentation? Is that the presentation?
Sì. Dov'è la chiocciola? No, qua. Dice che non ce l'ha. Non va. Quindi ho detto di mandarmela. Ancora non prende la connessione.
This third presentation, can I copy to this PC?
Yeah. You're connected. Sorry. It's your email.
Okay.
Yes, it's mine.
Okay.
Okay.
The other one is already.
Yeah, it's in the USB. Yeah.
I think
You can remove.
your folder.
It's in this folder.
Yes, the third one.
In the.
You can remove the USB.
Is this, no?
Yeah, the third one.
Yeah.
Third one. Okay.
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 Thank you.
Okay. So.
Can you start? So, we start the session. Unfortunately, Professor Teresa Guarda wasn't able to participate because he has technical problem. So the first presenter is Kwon Kwok and Gan Pam, high throughput FPGA-based elliptic curve digital signature core for IoT edge platform. Yeah.
Okay, yeah, thank you so much for the introduction. So, good morning. So my name is Go from Wook from Ho Chi Minh City, University of Technology in the south of Vietnam. So we are in the north of Vietnam, the capital. But Ho Chi Minh City is the biggest city in Vietnam. So today it's my pleasure to present our paper done by me and my students, my master students, Michigan. So the paper entitles High Throughput FPGA-based Elliptic Curve Digital Signature Core for IoT X platforms. So in this talk,
Doesn't work?
maybe we need to connect this one. What?
Yes.
Yes.
Okay.
Here the outline of talk today. At first, we make introductions and then the background of ICCSA and DNA digital signature algorithm, and then we show you the proposed architecture based on FPGA so that we can improve the throughput of DNA processing, and then we show you a prototype platform in a real system, a real FPGA board. Then we show you experiment, and finally we conclude our papers. So here the motivation, as you may know, according to Statista, in that year, maybe there is over 75 billion interconnected IoT devices. And because a large amount of devices connected to internet, so we need to do a lot of work for improving security solutions, especially for those devices. However, the big problem with those devices is the power, computational powers, because they are edge computing, they are edge platform, so it cannot be as good as, let's say, desktop or server or high performance computing system. And so that's why we need to do a lot of work so that we can improve security for the system. Because that reason, so in this paper, introduce the design implementation of ECC elliptic curve based digital system, digital signature algorithm, what we call ICCSA. And then we target the FPGA platform, one of the modern platforms, so that we can do prototype before we can make a chip with ASIC technology. So the main contribution of our work can be summarized into 3 different points. The first one, we introduce our efficient FPGA-based architectures for ECC by digital signature. And then we introduce the prototype system with an egg building with FPGA devices. It's very modern technology, very useful technology, along with a traditional processor or ASIC. And finally, we provide some experimental results for comparison in the future. Future study can compare with our work. At first, we show you the digital signature, elliptic curve-based DSA. There are 4 steps we can do to size a message generated by our system, so that the receiver must show that the message is sent from an authorized users. It's not a fake message, it's a trustable message. The first step, the sender needs to generate a key, both key, private key, and public key. And then the message will be hashed by some algorithms. In this work with ECC base, we use SHA-256. And after that, we size the message by using the elliptic curve right numbers and some point based on the private key. And after that, the signed message will be sent over the internet. So then the receiver will use the public key to verify if the message signed by the authorized users or not, or after signing, is there any modifications or not. If the receiver verify that it is produced by authorized users and nobody modified the message after sign, the receiver can use that message for their purpose. Right? That in general, so based on the step here, so we propose architectures that we use hardware accelerator approach. It means that we need a hot processors for doing traditional software step like graphic user interface, receiving message from sender, and then after that we have accelerator core. The core will be processed and done by FPGA technology. So inside the core, you see we can have some interface via bus, and we have some buffer, local buffer for storing the message, storing parameter, as well as the hardware core for computing SHA-256 hashing and generate the signature based on the flows we showed you previously. So this is because the hardware part of FPGA technology can be reconfigurable. It can be reconfigurable. So we can increase or reduce the number of signing core for improving the throughput, depend on how big, how good the system is. So if we have money, we can invest very expensive devices, and or we can have lots of resources. We can build many core. In case we apply for edge computing, so we can invest, let's say, $100 USD for the board computing system, so we can build 1 or 2 core. It is one of the most advantages of FPGA technology. We can reconfigure the system according to the available resources. General architectures in details, the hashing is very simple. The SHA-256 algorithm is very simple. We need only a table for hashing test. We don't show the architecture of the hashing here. we also only show here the ICCSA's signature generations core, where the two main block need to be yield, modular, addition, subtraction, and multiply. On the left hand side, we show you the addition, subtraction, modular by on algorithms, very famous algorithm. And on the right hand side, that the way for computing multipliers. So because we need 256 multipliers, so it's very time consuming in case we do sequential multiplier. So now we divide into two different. We divide into small block 138, and then we multiply in parallel, and at the end we get the result faster. However, of course, the drawback of this approach is the huge high result usage. However, as I told you before, one of the advantages of FPGA device is the amount of results available. Now we can exploit that amount of result for improving the throughput of the system. And then we build the architectures we proposed before on a real system, the silent carrier KB 260 board. The cost of this board is very reasonable, about 200 USD, very useful. It's very reasonable for deploy edge computing. Let's say for smart home or smart building or some other purpose for smart classrooms or university. So in this case, since the cost for the board is reasonable, so we can build two core, two Hasin cores, and silent cores. Inside this system, there is an ARM processors, ARM Cortex processors, A50, and it's connected with hardware core via AC bus, a special kind of bus from silent manufacturers. And then we build two core so that the message can be processed and signed concurrently. We can improve the throughput. Then we do synthesize process, and here is the synthesize process report from the tunes. Our system can work with 160 megahertz. It's very good for edge computing because in edge computing the frequency is usually small, so that we can save the energy consumption. The power consumption in our case is 3.1 watt. It's good enough for battery-based system. So you see, if we deployed two cores, we yield up to 52% of the available result, half of the process and the device is the board. If we only one core, 27.5% ratio required, different type ratio. And here we compare our work with related work in the literatures. We use the test vectors provided by NIST, National Institute of Standard Technology. So as you may see here, we outperform all the reference work in terms of the number of signatures can be done per cycles. Right? For our work, we can generate 2 times faster than the most highest one in the literatures. The latencies for generating signatures is about 0.5 milliseconds because we have 2 different core. It's very good result compared to literature. But of course, in terms of edge computing, we compare with edge computing platform only. We cannot compare with high performance computing because, of course, we have different purpose and different targets. So that all of our presentation. So in conclusion, In this work, we already proposed efficient FPGA based ECC digital signature hardware core so that we can increase or reduce the number of hardware core based on the available resource on the other devices, the hardware devices, so that we can deploy in different situations. We make a prototype version on a silent carrier edge computing platform and achieve good result compared to related work in the literatures with 2 times better in throughput. That's our presentation. So thank you for your attention. Happy to answer the question.
Any question?
This system has been used in some hardware.
Yes, we need some hardware for building the system because our work based on FPGA, that's special hardware technology. So similar, it's a chip similar to your CPU or a network chip. However, the chip can be reconfigurable technology. Because it's reconfigurable, you see, we can change the number of core here. The number of core change will depend on how big, how good the chip is.
Thank you. Very interesting presentation. Which is the programming environment you use for FPGA?
We for the language we use hardware derivation language, Verilog or VHDL, and then for the tune change, it is Vivado tune chain provided by the FPGA supplier. Decided they have a special tune chain. We can use we can divide the circuit, the hardware core by hardware derivation language. Nowadays we can use C++, but it's not sufficient compared to it is not as good as hardware derivation language.
Okay. And any attempt to using Go? Sorry. Any attempt to using Go programming language?
Go programming language. C++ programming language is usable. Yeah.
But Go you haven't tried, never. The Google language.
Not yet.
Okay.
We tried hardware derivation language only because usually it offers higher, better result because it's very close to hardware.
Yeah. And Go offer the advantage that is an open language. So okay. Thank you.
Okay.
Very
Thank
cool.
you.
Thank you. So we assume that the virtual presentation is missing.
Yes.
Since no one is connected. And the last presenter is Ryoha Umeda. Is it? Okay. The authors of the paper are Ryoda Umeda, Wei Wu, Yannan Hu, and Hideki Hashimoto. Sorry for pronunciation. The title of the paper is Exact Algorithms for Weighted Rectangular Covering Problems. Okay.
I'm Ryoda from Tokyo University of Science. I will introduce exact algorithm for weighted rectangular covering problem. First of all, let me introduce weighted rectangular covering problem. We are given a set of points P go from 1 to n. Each point I is coordinates AIDR, and the set of rectangle types are equal from 1 to t. Each rectangle types are with width WR, height HR, and weight CR. We assume that all input values are non-negative integers. The weighted rectangular covering problem aims to place rectangles with types in R on the plane to cover all the given points, such that the total weight of the used rectangle is minimized. For example, if we are given this set of points and 3 rectangle types, we can cover all points like this. The total weight is 3C1 plus C2 plus 2C3. In this study, we assume that there are enough rectangles of each type, and each rectangle must be placed without rotation, and each edge of the placed rectangle must be parallel to either the x-axis or the y-axis. For input value t and m, we assume that t less than or equal m to 4 because if t larger than m to 4, there exists an optimal solution using at most n to 4 times of rectangle. The rectangular covering has been investigated from 1980s. For the WRCP, Fowler and others demonstrated its energy hardness, and Position proposed an exact algorithm with time complexity of order n to 6 to n. We first introduced Position's algorithm. Position's algorithm is based on dynamic programming. Let FJRs be the minimum weight required to cover a set of points as subset equal P using at most J rectangles. Then the minimum value for FJP over J is the optimum value to the WRCP. For each subset else, RS is defined as a subset of all rectangle types in which each type can cover all the points in S. Then the boundary value F1 else for each else can be computed like this. For example, suppose there are three rectangles R1, R2, and R3, and the weights are given in this way. Then for such a set of points else, F1 else is the smallest weight that can cover us, so F1 else equals C2. To perform dynamic programming, Position's method first generates a set G as a subset of the power set of S. For every PR, PR, PB, PT in S, PR S prime is the set of all P in S such that APR less than equal AP less than equal APR and BPB less than equal BP less than equal BPT to GS. Based on FIRs and GRs, of JRs can be computed by the following recurrence formula. The basic idea is that an optimal solution to the subproblem corresponding to FJLs is able to be separated into one rectangle covering points in S prime, and the other is J minus one rectangles covering points in S set minus S prime. Computation of all values FIRs takes order Tn to 10, and all calculations of FJRs can be performed like this, and therefore can be done in order n to 6 to 10 time. Hence, the overall running time is order n to 6 to 10. Next, we propose a new algorithm that improves on Position's algorithm by adding a new method to generate GLs and a new dynamic programming approach. In Position's algorithm, we introduced a construction method to generate candidate GLs for solving the subproblem FGLs. We propose a new construction method that reduces the number of elements in GLs to order t times the size of L squared, if t less than the size of S squared. For every PR PB in S and rectangle type R in R, we add S prime is the set of all P in S such that APR less than equal AP less than equal APR plus WR. and VPB less than or equal VPT, VPB to HR to GRs. By selecting the more efficient construction method, the size of GRs can be bounded by order minimum the size of L default T times the size of L squared. Then we design a new DP method in which we consider a new type of subprogram. Let Fs be the minimum way to cover the point set Ls without any constraint on the number of rectangles. Note that this definition simplifies the definition of FGRs in Pontian's algorithm by omitting the number of rectangles. Value of FLs can be computed recursively as follows. Computation of all values FLs takes order Tn to Tn, and then all calculations of FLs can be performed by this, and therefore can be done in order minimum n to 5 to 10, Tn to 3 to 10. Hence, the overall running time is this. Even in the worst case, our algorithm can improve order n from Pontian's algorithm. Yeah. Next, let me introduce weighted line segment covering problem. Now, we consider the weighted line segment covering problem WRCP, given a set of points P as in WRCP, and given a set of line segment type R from 1 to T. Each line segment type R with length R and weight R, which can be treated as a special case of the WRCP when every given rectangle type has width or height of 0. Weighted line segment covering problem aims to place line segment with types in R on the plane to cover all the given points, such that the total weight of the used line segments is minimized. We proved that it is NP-hard in the strong sense, even if there are only one horizontal type and one vertical type of line segment with a length of 3 units. But we omit the proof because of time limitation. Then we propose an exact algorithm for solving the WLCP with time complexity of order Tn to Tn. We first consider a special case of the WLCP where all the points have the same x coordinate or y coordinate on the WLCP. This problem can be solved by using a two-pointer technique with time complexity of order Tn. Let S be a subset of P, and we consider two subproblems, PVRs and PHP set minus S. In the subproblem PVRs, the line segment types are limited to vertical line segments, and let GVRs denote the optimum value of PVRs. Similarly, in the subproblem PHP set minus S, the line segment types are limited to horizontal line segment, and let GHP set minus denotes the optimum value of PHP set minus S. Both PVRs and PHP set minus S can be further divided into several independent 1D CPRs. Hence, given that the number of all points is n, the optimal value GVRs and GHP set minus S can be obtained in order Tn. The proposed algorithm enumerates all the subset of P and outputs the solution with with the minimum weight as follows. By lexicographically enumerating with subset errors, the WLCP can be solved in order T1 to 2 time. Finally, let me introduce weighted by segment covering problem with unit length line segments. We prove that the WLCP in which the length of every by segment is 3 is n count. Now we investigated the case when every line segment has a unit length. We show that it is reducible to the minimum cost flow problem. In the MCFP, we are given a directed graph C equal VE with a source vertex VS and sink vertex VT. Each ij in E has an associated cost C prime ij that denotes the cost per unit flow on that edge. We assume that the full cost varies linearly with the amount of flow. We also associate with each hij in E a capacity Uij that denotes the maximum amount that can flow on the edge, and the lower bound Lij that denotes the minimum amount that must flow on the edge. The MCLP aims to send an amount of flow Q from VR to VT with a minimum total cost. Given a WLCP instance with endpoints, we construct a directed graph for the MCFP with n plus 4 vertices V. The n vertices correspond to the points of P and are divided into V even and V odd according to the evenness of AI plus BI. The remaining 4 vertices are VS, VT, V even, and V odd. The graph of WCFP is created by adding edges to this. First, for a vertex in group V even to a vertex in group V odd, select an edge with maximum flow rate is 1, minimum flow rate is 0, and cost equal to the weight of covering the corresponding 2 points. For example, the line segment covering points 1, 1 and 1, 2 is shown on the right. And the line segment covering points 1, 1 and 1, 2 shown on the right. By repeating this process, the edges are finally stretched like this. These edges image represent line segments covering 2 points. Next, from V even to the vertex of group V odd, extend the edges in even or maximum flow rate 1, minimum flow rate 0, and cost minimum C1 and C2. Similarly, from the vertex of group V even to V odd, extend the edges E odd or maximum flow rate 1, minimum flow rate 0, and cost minimum C1 and C2. E even and E odd correspond to line segments used to cover only 1 point. Furthermore, from VS to the vertex of V even and from vertex of V odd to VT, extend the edges of maximum flow rate 1, minimum flow rate 1, and cost 0. These minimum flow rates ensure that all the points are covered. Finally, straight the edges as shown on the right. The flow amount Q sent from VS to VT is set to Q equal N. The optimal value of the MCFP coincides with the optimal value of WLCP. There are various algorithms for the MCFP with polynomial time. Hence, the problem WCPUL can also be solved in polynomial time. In conclusion, this is what we found in this study. Thank you so much for your kind attention.
Are there questions? What are the possible application of your findings?
Practical application, possible practical application.
Yes, we have not considered its practical case yet, but our research is motivated by previous research in which some practical cases may be mentioned. In my opinion, the rectangle case might be used in fields like urban design. Consider the cases in which we want to decide the locations of bike sharing or bus stations. For the line segment case, in the design of printed circuit boards, it can be used to optimize the layout of components and wiring in some cases.
Okay,
Thank you.
thank you.
So this concludes this session. Okay, thank you for attending.
Dopo c'è, adesso c'è il break fino alle 11, giusto?
Tu sei sempre qui?
No, cambio perché devo presentare come faccio. Devo vedere. Non devo montare adesso. Io calmati.
Io sono in 5F. Tu?
5F. 5F. Ok, io sono in... Ah no, sono tutto il giorno venerdì.
Ok.
Però dovrei... non prende. Dovrei parlare. Devo presentare un paper, non mio figlio. Room G. Lei è?
Io sono in
Ok. Ok. Bene, quindi lascio questo, scrivo a Damiano. Ok. Di close. Di back. Ok.
Sì.